Assalamualaikum and hi. We are from Group 5. We'll be presenting Artificial Intelligence Project. And these are Group 5 members.
Hi, my name is Amisha and I will talk about introduction to BFS and DFS. So as we know, search algorithms are important in AI because they help us solve problems like finding paths and decision trees and etc. So in this project, we're focusing on two algorithms, breadth first search BFS and depth first search DFS. So BFS works by exploring level by level, starting with the nearest nodes and moving upwards. It's great when we need to find a shortest path in an unweighted graph. So, on the other hand, the FS goes deep into one path at a time before backtracking, making it better suited for exploring large or deep networks where the memory's usage needs to stay low. So, the aim of this project is we're comparing these two algorithms based on performance factors like speed, memory usage, and their abilities to find complete or optimal solutions. So we also make sure to use AI tools like ChatGPT during this project to enhance collaboration and learning.
Hello, my name is Ummie Najwa, and my task for this project is to do the code implementation for both algorithm DFS and BFS. So as you can see in the figure 1, it is the graph representation, and for figure 2, it is the Digiextra algorithm to find the minimum cost finder. So we use Digiextra to compare the optimality for minimum cost, where we compare Digiextra and for example, we compare Digiextra and BFS, and we compare Digiextra and BFS. So why we do this? It is because when we execute the program, Digiextra will know which is the shortest path. But for our BFS and DFS implementation, it will traverse the node just like the usual traversal. And please note that this Digextra is used only for comparison of the optimality, and it is not used for node traversal. And I will be moving for BFS code implementation explanation. Okay, so for main BFS function structure, the core component is it uses DQ for first in first out queue implementation, and it tracks performance metric such as memory usage and execution time, and it initialize visited set for cycle detection, and it counter for expanded nodes. Please note that BFS is using queue, which is first in, first out. For BFS main logic, it is a level by level exploration, and the path tracking is using queue. And this implementation is efficient for neighbor processing, and we integrate the cost calculation. While for BFS result collection, we collect path and cost information as well as the performance statistic and the optimality checking. For figure 6, it is a failure case written, and it is only executed if no path is found. But in our case, the return block is actually not executed because because the algorithm found the path from A to H. But it is important. This implementation is important because it is to return if no path exists. In figure 7, it is the BFS result printer, where we print the analyzed summary for BFS, where we print the result of path found, path cost, nodes expanded, the execution time, memory picked, the completion, and the optimality. Okay, moving on to the DFS implementation. It is using the similar setup such as BFS, but with some key differences where where DFS is using stack instead of queue, where stack is using last in, first out. And we are using the same performance tracking setup such as the memory usage and the optimality, where we are comparing it with Digiextra. In figure 9, it shows the DFS calculate path cost. It is using the same setup or structure as how we code the BFS. Another key differences of the FS implementation is we are using reverse operation. So for example, where we have the neighbor list of B and C, we will reverse it, and the algorithm will add C first and then B to the stack order. So when it will pop B first and then it will pop C. And why we use reverse? It is because stack is a last in first out algorithm, and without reverse it would process C first before B. And coincidentally, when we look at the graph structure, we notice that if we do the reverse operation, the algorithm will return the cost path of 5, which is optimal if we compare to the Dijkstra algorithm. So that is why we are doing it in reverse operation. But this result might vary if we traverse from other nodes to other nodes. Lastly, for figure 11 and figure 13, it is just the same setup for the FS result collection and the FS result printer, where we collect the result of the DFS algorithm and we print it for analyze. And this is the expected output from the code. Figure 14 is showing the output for BFS, and figure 15 is showing the output for DFS. Please note that the execution time and memory peak for both algorithms might vary every time we execute the code, but theoretically, the DFS code will always use less time and memory compared to BFS. And the analysis of this result will be presented further by my friend after this. So that's all from me. Thank you.
Hello, my name is Nur Hanisah binti Zain with the matrix number 85103, and today I'm going to present the key findings from the performance analysis for both breadth first search and depth first search algorithm. These are the key findings from the performance analysis of breadth first search algorithm. The algorithm found a path from A to H going through points A, C, F, and H. The total cost to reach the destination was 9. The algorithm only needed to check 8 nodes and took 0.000102 seconds to run. Memory usage was minimal at 1.9 kilobyte. Next, the algorithm successfully found a path which we call completeness. However, it didn't find the shortest possible path, which means it was not optimal. These results show that while our algorithm works reliably, there might be room to improve its path-finding efficiency. Now, this is our findings for the depth first search algorithm analysis. Our algorithm successfully found a path from A to H following the sequence A, B, D, G, and finally H. The total path cost was 5, which is notably efficient. The depth first search algorithm expanded only 5 nodes and executed very quickly in 0.000082 seconds. The memory usage was quite efficient at 1.14 kilobyte. Importantly, our depth first search implementation achieved both completeness and optimality, meaning it not only found a path to the destination, but also found the optimal path. These results demonstrate that our depth first search implementation is performing exceptionally well, delivering both efficiency and accuracy.
Assalamualaikum. My name is Nur Hanisah Ibrahim, metric number 85101. I will be presenting challenges in breadth first search and depth first search. For challenges in BFS, the first one is handling large graph. Large graph can overwhelm memory due to the storage of node, edges, and the queue used in BFS. Secondly, cycle detection. Cycles in the graph can cause infinite loop if not handled correctly. Third, path cost calculation. Calculating the total cost of path in weighted graph is complex because BFS prioritize breadth over cost. Fourth, comparing BFS with optimal algorithm. Verifying BFS result against optimal solution like Dijkstra's algorithm add a layer of complexity in validation. Fifth, performance metric tracking, measuring execution time, memory usage, and completeness during runtime while keeping the implementation efficient is non-trivial. Next, challenges in DFS. First, excessive recursion depth. In recursive implementation, deep recursion can lead to stack overflow, especially in large or dense graphs. Then, backtracking and cycle handling. DFS relies on backtracking, which can re explore nodes unnecessarily if cycles are not handled. Third, path and cost management. Tracking the path and calculating its cost dynamically is challenging, especially with weighted graphs. Fourth, optimization validation. Verifying whether DFS provides an optimal path requires comparison with algorithms like Jigtrust. Lastly, performance analysis. Accurately measuring execution time, memory usage, and the number of nodes explored while avoiding performance degradation. This project focused on implementing and comparing breadth first search and depth first search algorithm was a valuable learning experience. It helped us understand how these algorithms work, their strengths and their weaknesses. We faced challenges such as figuring out why BFS and DFS are not the best for weighted graphs and managing memory efficiently, but we overcame them with research, teamwork, and support from AI tools. Working together as a team taught us the importance of clear communication and dividing tasks effectively. Each team member played a key role, which made the final work detailed and complete. Using AI tools like Cloud AI and DeepSeek helped us solve problems faster, but we also learned the importance of checking and understanding their suggestions. Overall, this project improved our coding, problem solving, and teamwork skills. It also showed us how to use AI responsibly and effectively. These lessons will be helpful for our future study and careers in computer science. That is all from our group. Thank you.